In March 2026, a man walked onto a stage in Shenzhen, holding a piece of hardware no larger than a paperback book. He held it up to the lights, a single silicon card called the Atlas 350. To the untrained eye, it looked like a standard component you might slide into a high-end gaming PC. But it wasn't. That single card packed 156 petaflops of artificial intelligence computing power. Let's translate that number into something tangible. That is 1.56 quadrillion calculations occurring every single second. It is the raw processing throughput of roughly 150 top-tier consumer laptops compressed into a piece of metal and silicon you can hold in one hand. More importantly, it is nearly 3 times more powerful than the absolute best artificial intelligence processor that the United States government still permits American companies to sell into the Chinese market on its own. That performance jump is a massive story. It represents a direct challenge to geopolitical trade restrictions and a sudden shift in the balance of technological power. But the sheer speed of this chip is actually the least interesting thing about it. The true disruption lies in how it came to exist in the first place. If you ask any semiconductor analyst or Silicon Valley executive how to build an advanced artificial intelligence accelerator, they will give you a very specific, highly complex recipe. They will tell you that you absolutely require a multi-billion-dollar fabrication facility. They will tell you that you must have extreme ultraviolet lithography machines from the Netherlands. Machines so intricate they are practically considered miracles of physics. They will tell you that you need ultra-dense, specialized memory modules manufactured by a tightly controlled duopoly in South Korea. And finally, they will tell you that without a massive, decades-old American software ecosystem to tie it all together. The hardware is nothing more than an expensive paperweight. The global tech industry operated on the absolute certainty that if you cut off access to even one of these ingredients, the entire recipe falls apart. It was a consensus built on physics, economics, and logistics. Yet, when you tear down the Atlas 350, you discover something that fundamentally defies that logic. There is no Dutch lithography involved in this silicon. There is no South Korean memory soldered to the board. There is no American software running the instructions. The entire stack, from the raw architecture of the transistor gates to the lines of code communicating with the neural networks, was built using tools and supply chains that the rest of the world assumed were completely inadequate for the task. Just 8 days before the massive artificial intelligence model designed to run on this hardware went live, the chief executive of NVIDIA openly stated that the scenario unfolding in China was a horrible outcome for American tech. He wasn't exaggerating. To understand how a single product launch managed to cause panic across the Pacific, you have to look at the artificial ceiling that was supposed to keep this exact moment from ever happening. When international export controls tightened, the strategy was elegant in its simplicity. Instead of completely cutting off the second largest economy on Earth, American chip designers were forced to create heavily modified, deliberately throttled versions of their flagship processors specifically for Chinese buyers. The most prominent of these was a chip called the H20. The H20 was engineered with a very specific purpose. It was designed to give Chinese technology companies just enough computing power to handle everyday cloud operations and basic data processing, while ensuring they remained completely incapable of training the massive frontier-class artificial intelligence models that define the current technological era. It was a digital speed limit, a regulatory wall that every policymaker in Washington believed would hold for years to come. The Atlas 350 didn't just breach that wall, it completely demolished it at 156 petaflops of specialized processing speed. A single one of these new cards delivers nearly triple the data throughput of the American chip it was meant to compete against. It carries 112 gigabytes of high-bandwidth memory moving data at a staggering 1.4 terabytes per second. But the real pressure point isn't just performance, it's the economics. Huawei priced this hardware at roughly $16,000 per card. If you look at the procurement budgets of major technology conglomerates, that is the exact same price bracket they were already allocating for the restricted American chips. The market response was almost instantaneous. Within weeks of the announcement, the largest internet, cloud, and social media platforms in the region bypassed the restricted import options entirely and placed massive bulk orders for the domestic alternative. As a direct result, a massive shift in market leadership is occurring in real time. Revenue flowing into this specific domestic hardware line is projected to skyrocket to $12 billion this year, up from an already substantial $7.5 billion just 12 months ago. And yet, as the orders pile up and the data centers fill with this new hardware, the central paradox of the story only deepens. Because by every established rule of modern engineering, this chip should not exist. The machinery required to print features this small on a silicon wafer is legally blocked from entering the country. The factories capable of layering memory cells with this level of precision are completely out of reach. The entire Western semiconductor industry looked at the restrictions, looked at the available infrastructure inside China, and reached a unanimous conclusion. You simply cannot get there from here, and that is where the story stops making sense. Because they did get there, and the way they bypassed the global supply chain exposes a massive blind spot in how the world thinks about innovation under pressure. To see exactly how they pulled this off, we have to look at the physical layout of the silicon itself. Because what is printed on this wafer reveals a radical, desperate, and incredibly clever workaround that changed the rules of chip manufacturing entirely. When you zoom in on a modern artificial intelligence chip, you are looking at one of the most densely packed structures ever created by humanity. In a standard cutting-edge processor, tens of billions of microscopic switches called transistors are etched onto a piece of silicon no larger than a postage stamp. To achieve this, the global tech industry relies entirely on a process called extreme ultraviolet lithography, or EUV. Think of EUV as the world's sharpest stenciling tool. It uses incredibly short wavelengths of light to draw features so unimaginably small that you could fit thousands of them across the width of a single human hair. If you have an EUV machine, printing these hyperdense circuits is standard procedure. If you don't, the conventional wisdom says you are completely locked out of the high-end chip race. Huawei and its manufacturing partner, SMIC, did not have access to EUV. They were restricted to an older technology called deep ultraviolet lithography, or DUV. To understand the challenge they faced, imagine trying to paint a highly detailed, miniature portrait, but the only tool you are allowed to use is a thick, blunt Sharpie. The lines you draw are naturally wider, meaning you can't fit as many details into a small space. In the world of silicon, wider lines mean larger transistors, and larger transistors mean a physically massive chip that consumes too much power and generates crippling amounts of heat. So how do you achieve frontier-level performance when your stenciling tool is fundamentally too thick? You don't change the tool, you change how you use it. Huawei turned to a highly complex manufacturing workaround known as multi-patterning. Instead of exposing the silicon wafer to light just once to print a circuit layout, they exposed it multiple times. Shifting the stencil ever so slightly with each pass, imagine using that same blunt Sharpie to draw two parallel lines that are incredibly close together. You draw the first line, then you carefully slide your ruler over by a fraction of a millimeter, and draw the second line, so that their edges perfectly align to create a much sharper, thinner space between them. By layering these imperfect exposures on top of each other, with absolute atomic scale precision, they managed to trick the older machinery into printing features that approached the density of far more advanced manufacturing processes. But this workaround came with a severe physical penalty. Because the chip features had to be printed across multiple complex steps, the physical size of the actual processor die ended up roughly 60% larger than a comparable chip produced by NVIDIA. In physics, a larger chip is an inherently dangerous gamble. Silicon wafers are circular plates, and chips are carved out of them as rectangles. When you make each individual rectangle 60% larger, you fit far fewer of them onto a single wafer. Worse still, if a single microscopic defect lands on that wafer during production, it ruins a much larger percentage of your usable product. The industry term for the percentage of working chips you successfully harvest from a wafer is called yield. For months, Western analysts assumed that even if Huawei could print these larger chips, their yields would be so catastrophic that mass production would be economically impossible. Yet, they found a way to make the economics work. And that brings us to the second, even more shocking layer of this hardware teardown, the memory. An artificial intelligence chip is essentially a hyper-fast calculator, but a fast calculator is useless if it has to wait in line to receive the numbers it needs to crunch. This bottleneck is known as the memory wall. To break through this wall, advanced AI hardware uses something called high-bandwidth memory, or HBM. Instead of placing memory chips side by side on a circuit board, HBM stacks memory cells vertically, like floors in a skyscraper, and connects them using thousands of microscopic vertical wires. This allows data to travel up and down at blinding speeds. Historically, only two companies in South Korea possess the proprietary recipes and specialized factories required to build these vertical memory skyscrapers. When the supply chain was cut off, the consensus was clear. China could not replicate this technology from scratch. Huawei's response was to reject the existing blueprints entirely and develop a completely proprietary standard called HBL 1.0. They didn't just copy the South Korean design, they re-engineered the way the processor talks to the memory stack. When an artificial intelligence model, like a large language model, is running, it doesn't request data in neat, predictable blocks. It requests information in highly irregular, scattered patterns. In standard memory configurations, when the chip asks for a tiny piece of data, the memory architecture is forced to send a massive chunk of surrounding data along with it, simply because the delivery highway is built for bulk transport. This wastes an immense amount of bandwidth. Huawei altered the memory access granularity of HBL 1.0 down to 128 bytes. That is 4 times finer than the previous industry standards. Think of it like a mail delivery system. Instead of forcing a massive delivery truck to drive all the way across town just to drop off a single tiny envelope, blocking traffic and wasting fuel, Huawei built a fleet of hyper-efficient couriers that can deliver individual letters independently. This means that even though their raw hardware manufacturing limits prevented them from achieving the absolute highest top speeds on paper, the chip wastes almost zero time handling the messy, chaotic data streams that large language models demand. Every cycle of electricity is maximized. Every lane of the memory highway is perfectly utilized. Look at what this means for the anatomy of the Atlas 350. The core logic processor is printed using an entirely homegrown multi-patterning technique. The memory skyscraper sitting right next to it is a completely proprietary domestic architecture, and the ultra-fast interconnect fabric that allows these components to speak to one another is entirely self-developed. For the first time in modern technological history, a high-performance artificial intelligence accelerator has been built with an entirely self-contained supply chain. It is a triumph of engineering born purely out of structural isolation. But as impressive as this physical hardware reconstruction is, any computer scientist will tell you that silicon is only half the battle. You can build the most sophisticated, efficient hardware stack on Earth, but it remains completely inert without the software layer that tells the transistors how to think. And it is precisely at this software layer where the story stops being a localized manufacturing miracle and transforms into a global, systemic disruption. Because to make this chip useful, Huawei had to take aim at the single most powerful monopoly in the technology world. Here is the part that most people completely miss about the technology industry. It was never just about the chips. The silicon is crucial, but it is nothing without software. For nearly 2 decades, NVIDIA's real stranglehold on the artificial intelligence market hasn't been their hardware design. It has been an underlying software platform called CUDA. CUDA is the invisible translator of the modern tech world. It is the deep architectural layer that sits directly between the physical silicon of a graphics processor and every major artificial intelligence model ever constructed. Every single line of code that powers ChatGPT, Claude, Gemini, or Llama was written to speak natively to CUDA. To understand the sheer scale of this monopoly, imagine trying to move away from CUDA. It is not like swapping out a dead light bulb for a new brand. It is like trying to completely rewire every single wall, junction box, and outlet inside a 60-story skyscraper while the tenants are still living inside it. The friction is immense, the cost is prohibitive, and the risk of catastrophic failure is incredibly high. Because of this, almost every technology analyst on Earth assumed that even if China managed to clone American hardware, their software ecosystem would remain years, if not decades, behind. Huawei's domestic software alternative, known as CAN, was widely written off by the industry as immature, buggy, and completely impractical for high-end applications. And then, on April 24, 2026, a company called DeepSeek launched its next-generation artificial intelligence model, DeepSeek V4. The numbers behind this model are staggering. It features 1.6 trillion total parameters, operating with a native context window capable of processing 1 million tokens of data simultaneously, But the truly disruptive metric isn't the size of the model, it is its genetic code. DeepSeek V4 is the first frontier-class artificial intelligence system in human history to be built with absolutely zero dependency on NVIDIA software or hardware anywhere in its pipeline. NVIDIA Build It was not trained on Western processors. It was not optimized using CUDA. Instead, a dedicated team of engineers spent months completely rewriting the core mathematical kernels of the network to run natively on Huawei's Ascend hardware using the domestic CAN software platform. When the model went live, major cloud providers like Alibaba Cloud and Tencent Cloud deployed it across their networks within a matter of hours. Step back and look at the structural reality of what now exists. The processor is domestic. The vertical memory stack is domestic. The underlying software framework is domestic. And the frontier-class intelligence model running on top of it is entirely domestic. For the very first time since the dawn of the digital age, a complete self-sustaining computing civilization has emerged that owes absolutely nothing to the American technology ecosystem. It is a parallel infrastructure built under total isolation, and it functions at scale right now. When you look at this development from a strategic perspective, it reveals a massive historical paradox. International trade sanctions are traditionally designed to achieve a very simple outcome: to isolate a competitor, restrict their access to critical tools, and slow their technological advancement by a decade or more. You cut off the supply of advanced lithography, you block the import of South Korean memory, and you wait for the target to freeze in place. But that strategy assumes the target has an alternative place to go. When you completely close every single door to the global market, you remove the luxury of choice. You replace market economics with raw, existential necessity. Before these restrictions were put in place, major Chinese technology companies had very little reason to buy domestic silicon. Huawei's early chips were harder to program, and their software ecosystem was unproven. It was vastly easier, safer, and more profitable for these firms to simply write a check to NVIDIA and plug into the global standard. The sanctions inadvertently killed that option. By legally banning American tech giants from selling their best hardware into China, the restrictions forced the entire domestic internet economy to become Huawei's ultimate R&D testbed. The results speak for themselves. In less than 18 months, one of the largest artificial intelligence hardware markets on the planet shifted from nearly total dependence on Silicon Valley to a state of rapidly accelerating self-sufficiency. The consequences of this shift are starting to reverberate through the entire global financial structure. NVIDIA's chief executive recently confirmed that their market share in China has dropped precipitously, effectively wiping out a market segment that analysts estimate was worth roughly $50 billion. That revenue isn't just paused, it is permanently gone, redirected entirely into funding the next generation of domestic semiconductor research. We are no longer looking at a world where one superpower leads and the rest of the world attempts to catch up using the same tools. The landscape has fundamentally fractured. Today, we are witnessing the birth of two entirely separate, highly competitive technology futures developing on completely opposite sides of the Pacific Ocean. One stack runs on NVIDIA, CUDA, and global supply chains. The other runs on Huawei CAN and entirely self-contained domestic manufacturing loops. They are two distinct digital ecosystems, driven by completely different geopolitical realities, and the physical distance between their capabilities is no longer widening. It is closing fast, but this entire parallel ecosystem relies on a fragile, razor-thin foundation. To keep this massive infrastructure running, Huawei has to produce these chips by the hundreds of thousands, using machinery that was never designed to handle that kind of load. Which raises the final, most critical question of this entire saga. How long can a parallel technological civilization survive when its entire manufacturing base is running on borrowed time? This brings us back to the image that started it all: a single silicon card held aloft under the theater lights of a Shenzhen stage. When we first looked at the Atlas 350, it seemed like a standard story of a corporate underdog pushing past a competitor's benchmark. But when you trace the lines from that hardware back to the machinery that printed it, the factories that stacked its memory, and the software that dictates its logic, a completely different reality emerges. The global technology market was built on a foundation of absolute interdependence. No single nation, no matter how vast its resources, was supposed to be capable of owning the entire semiconductor supply chain. The sheer material cost, the scientific complexity, and the specialized knowledge required to build an advanced artificial intelligence accelerator were believed to be the ultimate safety net. A global web where every participant was tethered to everyone else. The export controls deployed by the West were designed under this exact assumption that by clipping a few vital threads of that web, you could effectively anchor a rival's computing future in place. What the architects of those restrictions failed to foresee was the unintended consequence of absolute containment. When you cut off every avenue of access to an existing ecosystem, you stop protecting your technology. Instead, you inadvertently grant your competitor the most valuable asset any innovator can ask for: a captive, guaranteed domestic market with zero external options. The Atlas 350 is not just a faster product designed to fill a temporary gap in the Chinese internet landscape. It is the proof of concept for a completely independent technological ecosystem that has learned to survive and thrive entirely within its own borders. But this sudden leap forward does not mean the path ahead is clear. The real drama of this story is just entering its most volatile phase. By pushing older deep ultraviolet machinery into the realm of hyper-complex multi-patterning, Huawei and its partners have successfully closed the performance gap on paper, but they are doing so at an immense physical cost. These legacy machines are being driven far beyond their original engineering limits, running continuous multi-step exposures that naturally degrade component lifespans and keep manufacturing yields on a knife edge. The parallel computing civilization that China has built is functioning at an elite level right now, but it is effectively running on an infrastructure under extreme mechanical duress. It is a system built on sheer engineering willpower, functioning as a massive, high-stakes gamble against time. The question is no longer whether they can design advanced AI systems under isolation. They have already proven they can. The real question is whether their domestic fabrication plants can scale up production fast enough to meet the staggering demands of an entire economy before the strained infrastructure beneath them begins to buckle. As we watch this shadow race play out across the Pacific, the most surprising truth is that the old tech landscape is gone, and it is never coming back. The dream of a single unified global tech standard has officially fractured into two distinct realities. On one side stands a system built on global cooperation, optimized for efficiency and bleeding-edge scale. On the other side stands a parallel world built entirely on raw necessity